Hello. In this video, we're going to introduce the notion of Cauchy sequences. These sequences are fundamental to the study of real analysis at the undergraduate and graduate level and have implications in a lot of scenarios. So first, before defining what a Cauchy sequence is, I want you to consider the sequence that we all should be familiar with by this point. 1 over n. Okay. Now, in previous lectures, we've shown that this sequence converges. It's bounded, it's monotone, but in particular converges to 0 as n increases, right? So if we just kind of look at the real number line and study the behavior of this sequence as n increases, we'll start to notice something just by the picture that we draw. So for example, there's 1. It's the first term of the sequence. Maybe here is like a half. And then maybe a third. Fourth. A fifth. And I'm just gonna keep on doing this. And as we've seen before, as n increases, this sequence is definitely tending towards 0. It converges to 0. But I want you to notice something about the terms of this sequence. Notice that, for example, it looks to be the case that the distance from the, say, 4th term, so 1/4, and the 3rd term, it looks like that's smaller than the distance from, well, it doesn't look like it is smaller between the 2nd term and the 1st term. Isn't that true? Right, like, look, we have, that's the distance there, and then look how much smaller the distance is. Now, it's also the case that, oh, actually, the distance from x5 to x3 is also smaller than that distance, right? There's that distance, at least like pictorially it is true. But so, okay, let's imagine that we're varying the indices between here and there. Like this, we're curious because we're noticing that these things are smaller, right, than this distance here. And in fact, the distance between these two is less than that. The distance between these two is less than that distance. So maybe we can like ask ourselves by observing this pattern, so how does this behave? What does this do? For large n and m, as we vary these things, right? For large n and m, and they're just not going to depend on each other. We're just going to say, like, because here we fixed 3 and we varied the other index. So what's going on here? It looks like down the line, somewhere over here, these terms they're getting like squished together, right? Isn't it? It seemed that at some cutoff, all the terms are kind of like really small distance apart. it looks like the terms seem to be squishing together or squeezed together over here. Right? Like they're all, regardless of like xn distance to xn plus 1, it looks like if xn is like right there, then xn plus whatever is going to be close to it, right? So this motivates a definition. Observing this type of behavior for this sequence, you would also observe this type of behavior for other sequences. So whenever mathematicians encounter something that tends to appear over and over and over again, they like to define it and then study how that definition interacts with all the other theory that they've built. Okay, so let's define it. I think this is called, from the textbook that we're using, 3.5.1 definition. Okay. This is the notion of being a Cauchy sequence. So, a sequence x equals to xn of real numbers is called Cauchy if it does this, right? If those terms get squeezed together arbitrarily small whenever you take big enough indices on that sequence. So before I write the rest of it, think about it, right? Like, how do we determine closeness amongst real numbers on the real number line? Typically have some positive epsilon and then absolute values, right? Absolute values. Well, that's what we're going to do. So a sequence X of real numbers is called Cauchy. They're called a Cauchy sequence. Can you guess what kind of condition we're going to put on our epsilon besides being greater than 0? Not existence, but for every, right? So a sequence X is called a Cauchy sequence if for all epsilon greater than 0, there is some index, or there exists, I'll call it H, which again is just an index cutoff for the sequence, so that the absolute value from xn, so the distance from xn to xm is less than epsilon whenever n and m are greater than or equal to h. In other words, when we're picking the indices of the sequence large enough, all of those terms get squeezed together arbitrarily small, at a arbitrarily small distance from each other. This is a definition of Cauchy sequences, a very important definition, especially for those of you wanting to go to graduate school. And when you start studying what are known as metric spaces and the idea of a compact space or even a complete space. And these are things that are well above what we're covering in this class, but this definition is core to those concepts or fundamental to those concepts, those those fields of study. So this is the definition of Cauchy. I gave you this example as motivation. We should be able to show that this is a Cauchy sequence, right? So what do we want? So let's say that maybe the problem at hand is to show the sequence 1 over n is Cauchy. Let's see if we've written the definition in the correct manner that captures this idea of these terms getting closer and closer. So before I do that, maybe I'll have like some scratch work right here. What do I want? I want the terms to get close for large indices, and I don't want these to depend on each other. I just want them to be bigger than some cutoff index where after the sequence cuts off there, all the terms are within some small epsilon distance of each other. So what do I want? So this is again like scratch work. I want for that, I want this. I want to consider that, which is like 1 over n minus 1 over m, which if you add and subtract 0 to the middle, and you apply the triangle inequality, you'll see that this is at most this. Right? But this is like equal to, because these are just natural numbers, this. Okay. And we want this to be less than epsilon, right? So I can see it right now that if 1 over n is less than 1 over m, which is less than epsilon, and 1 over m, epsilon over 2, because I'm going to add those epsilons together. Again, constants don't matter when you're multiplying an epsilon because it's arbitrarily small, but just to make it look nice. Oh, no, not m. We're using h. Sorry. And then 1 over m less than or equal to 1 over h less than epsilon over 2. If these things hold, then this, which is less than or equal to 1 over n plus 1 over m, then that is less than epsilon over 2 plus epsilon over 2 equal to epsilon. So this is like my scratch work. This is what I want. So now we can use the scratch, come over here, and then actually show that this sequence is Cauchy, satisfies that definition. So let's look at the proof of this. So we're going to say, let epsilon be greater than 0. We got to be careful. So if m is greater than or equal to h, then this is true. That's like that part. So what I want is h to be greater than 2 over epsilon. It looks like, right? If I multiply both sides by 2 and divide by epsilon, multiply both sides by h, I'll have my choice of that cutoff h. So let epsilon be greater than 0, and maybe choose the natural number h so that h is greater than 2 over epsilon. H is greater than 2 over epsilon. Hence, epsilon is greater, epsilon over 2, made it all messy. Well, I hate it when that happens, but okay, so hence, epsilon over 2 is greater than h. Thus, if n and m are greater than h, we observe that the absolute value x of n minus x of m, which is less than or equal to, oh, I'm just making a mess all over the place. Well, no, I can go ahead and keep that actually. It's a little bit more instructive. This is actually equal to 1 over n minus 1 over m, which that's less than or equal to 1 over n plus 1 over m, right? But if n is greater than or equal to h, then 1 over n is less than or equal to 1 over h, and m is greater than or equal to h, so 1 over m is less than or equal to 1 over h, which is less than, so, oh, almost messed it up there. 1 over h, right? If I divide both sides by h, so 1 over h is strictly less than epsilon over 2 plus epsilon over 2, and that's equal to epsilon. So the distance between xn and xm, the sequence, is at most epsilon when n and m are greater than or equal to h, where h was chosen greater than 2 over epsilon. Since epsilon was arbitrary, we're done. We can just say hence that sequence 1 over n is Cauchy. Done. Okay. So that's nice. It seems to match up with what we were trying to begin with over here. Right? We wanted to somehow find a definition that appropriately suited how we can observe these terms just all getting jumbled up, squeezed together. We have this definition, and then we showed that that sequence does indeed satisfy that definition. Okay, so now that we've done this, I should probably tell you what the next videos will be about. In particular, we're going to establish that convergent sequences in R are precisely Cauchy sequences. We're going to show that if you're Cauchy, you're convergent in R, and if you're convergent, then you're also Cauchy. And that's what the next series of lectures or video recordings will be. Thank you for watching.